All right, so welcome to everybody that's joining us on YouTube. If you couldn't make it, today is March 26th. So a few people showed up, and we didn't have so many questions about the trigonometry stuff, so we're going to go ahead and jump in and do a little tutorial on the video here for our project. And so you can see I'm starting here with a blank, blank window. And the first thing I did is I took a screenshot of my face, and I am going to upload it here. Okay, so just now I took a screenshot, and we're going to see how we can trace some of this stuff. Okay, so Gabe, you had a question about eyes, right? So how can we trace eyes?
Yeah.
And so one of the tricks that I use a lot is the vertex form of a quadratic function. And so if I think about this, right? So I'm going to use the annotate feature. If I think about this, if I look at the top of my eye, it's going to be something like this. So can you all see what I'm drawing here?
Yep.
It's going to be something like that. And if I were to continue that out, it seems reasonable that that might be part of a parabola. Right. So if it was like this, right? So if I kind of kept going, it seems like that's not unreasonable that we might be able to fit the top of that with a parabola. And so if I want to make that parabola, I know right here that like I would want to make the vertex of my parabola pretty much right there, right? Maybe a little bit higher than that. So what I would do is I would go in my calculator and I would go and try to find that point. And so to me, it seems like right, the x coordinate is maybe something like right around here-ish, and the y coordinate is right around here. So if I were to guess at this, right? So I need to go back out of this. So it would be something like negative 1.4, comma 1.4. Okay. So this is a little bit less than that, right? So maybe like this 1.3, 1.4. And so we could adjust this up or down, but that's pretty close to where I wanted it to be, right? So if I wanted it, I could make it a little bit higher if I wanted to, right? And so if we really want to dial it in, we could, we could do something like this, right? And so this seems to be my exact point, right? So let's go ahead and let's clear out all my annotations here. So I have this, and what I want to do is I would like to make a parabola that goes through that point. So we know that our vertex form is this, right? So at like y equals a, x minus h squared plus k. This is what we saw with quadratic functions. And I know that the vertex is going to be these two coordinates. So h should be negative 1.33, which makes this a plus 1.33. And then this should be a plus 1.42. And now I don't know exactly what a is going to be. But what I can do is if I hit add slider, then it gives me this nice feature where I can sort of bend it around, and I can figure out what that a value is. So if I bend it to be, say, right here, it seems like, that seems like a reasonable curve to match the top of my eye. So what I'm going to do is I'm going to make this negative 0.5. So that's just my fixed function now. But I don't want all this over here. Okay, so again, if we go ahead and we annotate, right? So I'm gonna draw on the screen again. It seems like what I want is I would want to cut off. I would want the green line to stop maybe here, and then I would want to stop like maybe here. Right? Maybe we want a little bit more, a little bit in on that, something like this. And so what I could do is I could come over here and say, all right, let's go ahead and let's cut it off at those points. So it seems we're at negative 2.9. Sorry, negative 1.9 is less than x, right? So that cuts it off there. And then it seems like I want to go to maybe negative 0.8, something like that.
Yeah.
And so as I'm doing the I here, we can see that right, we can clear this out, and then when we click back into our graph, I don't need this point anymore. So now I've done the top, right? So I've done the top part of my I.
Mm-hmm.
And we could do something similar. I could even use this point again, right? So same x coordinate, but if I change my y coordinate, if I make it, say, like 1.1, that seems like that's the bottom of my I. Okay. And so what I could do is, a nice feature in Desmos is if you click on this gear right here, instead of typing all this out again, I could duplicate it and then just change it. So instead of this, I would want this to be a 1.1. And then I'm going to add my slider back in here again. Right, so now I can bend this around until I get it to about where I want it to be. Okay, and so it seems like if I make this equal to 0.5, right, then what I've done is, now with all of this here, right, I have what is reasonable for an I. Right, and so if we wanted to, we could continue these, right? We could continue these out until they met, if you wanted to do that.
Mm-hmm.
Okay. So the other part of the I would be this, right? You'd actually want your I there. And so remember that earlier when we were studying trigonometry, we looked at circles. So we have circles have this equation: x minus h squared plus y minus k squared equals r squared. And so if I can figure out what that center point of my I is and what the radius is, I should be able to use this equation. And so I think if we do negative 1.33 again, that would be the center. And then let's try 1.3. Right, so that looks pretty close to the center of my I. So I would use this for h, right? So this would be plus 1.33, and then k would be minus 1.3. And so let's make this something we can actually see here. We'll make it green. And so again, if I want to figure out what that radius is, I could make it so it doesn't like, so Desmos doesn't like r, uses it for something else. But right, so I could make it 0.1, right? You know, you can make it 0.11, 0.12 or something, right? And so if we zoom out from that, right, that seems like it's modeling an I reasonably well. Right, so it's not going to be perfect, but I would say that that would be a pretty good start, right? And then you would have an I there. And so for most of this, I think you're going to be able to get away with a lot of, you know, straight lines, right? So if I wanted to do sort of the side of my face here, it would be a straight line. The top of my head might even be a circle or a parabola. And then, you know, again, more parabolas if you do eyebrows, parabolas for your mouth. And so a lot of the time when students do this, you get a lot of this here. Now for my beard or something, if I wanted to, you know, if I wanted to make squiggles, I might do something like a trig function in there. Okay. So I'm going to kick it over to you all. Is this helpful so far? Do you have any questions about it?
Yeah, no, it's helpful because I was even thinking about using those equations for it, so that'll help a lot.
Yeah, so this would be like, so the idea behind this is, we have some sort of real world situation, right? So here's a picture. And one of the things that you probably have heard people say is, hey, math is all around you, right? There's math everywhere. And,
Mm,
you know, you might push back against that and say, well, hey, like, where's the math? Where's the math in my face? Or where's the math in the table or something? And so
yeah.
through pre-calc, calc, and calc 2, when I teach it, we do different modeling problems like this where we take, so in this class, we do modeling where we sort of trace designs. In calculus, we do some, we take like common logos around that we find around the world, and we find their area, we model them in Desmos. And then in Calc 2, we do volume. So we do 3D modeling of solids when we see the math
Mm-hmm.
behind all that. Yeah, so this shows you that, hey, we can actually model the world around us with mathematics.
Yeah, that's cool.
So how do we use the trig functions for this?
So, like, what do you mean? How would you use them?
Yeah, like how do you graph them? Do you just
Oh,
do like sine x?
Sine x. Yeah, if you wanted to graph something like this.
Yeah, now can you manipulate that, or is it just there? Like, can you move it around?
Yeah, so we can scale it. So generally, what we can do is we can scale it. So if we put a coefficient out front here, we can bend it sort of up and down.
Okay.
If we put a coefficient in here, we can sort of stretch it. B is going to stretch it left and right like this. So this B stretches it. Okay. And then if we add a transformation in here, if we add a C, then we can shift it left and right. Okay, so say I want it to be a little cartoony and maybe make myself sort of a crazy mustache, right? So I could bend it. I could bend it like this, where I could even add on to this slider. I can make it like 100 or something, right? So I could make this, like crazy mustache. Oh, and if we have a plus D on the outside, then we can shift it up and down. So I could give myself like a crazy mustache here and then cut it off at, looks like, negative 1.1. 0.5 or something like this. Right?
Okay.
So I could give myself, a little cartoony, but I think you get the effect if you wanted to use it, right? So alternatively, right, if I wanted to give myself some hair, right, do this, or you might be able to make it an eyebrow or something. You have to change your bounds here, but right. So I could do like a squiggly eyebrow or something like that.
Mm-hmm.
Okay, and that works for the other ones too, like cosine and cotangent.
Yep. So generally, this is going to be the transformation for any function, right? So you multiply on the outside like this, it's going to stretch it up and down. Multiply like this on the inside, it's going to stretch it left and right, horizontally. And then when you add and subtract these things, this is going to shift it left and right, and then outside is going to shift it up and down.
Okay.
It's kind of like the same thing that we're seeing over here. So this is the adding on the outside. So if you change this, it shifts it up and down. We saw this is the adding and subtracting on the inside. It shifts it right and left. And then this is the combination of this A and B that are bending, right? This bends our quadratic functions.
Okay.
All right, other stuff here. So this is helpful for you, Nick.
Mm.
Yes.
All right, what else do we got?
Are there any more functions that we can use besides those three?
Yeah, so we cited linear functions, quadratic functions, all the different trigonometric functions. We have circles. If you want to, so we saw, so let's add another one here, right? So we saw circles are x minus h squared plus y minus k squared equals r squared. Okay, so
Mm.
this gives us a circle. Right? Again, let's make it something that we can see. So it's green. So it's this circle that's over here. So right, if I drag this left and right, or if I drag it up and down, we can see I get that circle there. Okay, but if you want to, if I take this whole thing and I divide by, say, 2 or 3, see how it starts to deform my circle like this?
Mm-hmm.
Right, so if I divide by 5, you can see that we're stretching in the x direction, right? So we're dividing this by x. And then if I did something similar, if I went over here and divided my y by, say, 5, it would stretch it in the y direction. So if you wanted to, this is called an ellipse. It's almost the same equation as a circle, except we have an additional coefficient under here. And so we could also divide both of them, right? So if we did something like this 2 and 5, or 7, we could sort of bend it around into different shapes. So if you wanted to, you might find that it's a better fit to use an ellipse for some parts of your face, and that would be okay too, right? So I might have like an elliptical head here. Right, so like 12. Right, so you might find something like this, right, where you can model the top of your head with an ellipse or something. I think you're probably going to have better luck using the quadratics.
All right.
So yeah, between circles, ellipses, and then what we'll see today, we're going to start exponential functions. We'll see what comes out of that. So I'll kick it back to you again. Other things about graphing or tracing your face?
No, not really. That's about it.
That's pretty good. Did you all get to check out the Plato page where we have some examples? So
Yes.
So yeah, on our Plato page, I posted some examples here, so you can see what some other people have done in the past. Right. So this is a self-portrait that we had a few semesters ago. Okay. And here's another one. So.
Oh, that doesn't look that bad. It looks pretty good.
Yeah, they look pretty good, huh? So you can.
said,
So if you want to see them all, but you can check them out and sort of see what sort of other people did. So you can see in this one, right, they use a circle for the eye, and then some more circles, lots of quadratics, right? So quadratics, these are circles. These are just lines, right? These are just straight lines. Right, so lots of those, lots of straight lines. More quadratics, right? So here's a lot of quadratics and circles. So I think it might be all right. And here's some log functions. So we'll see those. We'll see these. So she used some logs here, and so these are logarithms. We'll see those next week. I'm not sure that she used any exponential functions. But yeah, most of these are just linear functions, quadratics, and a few logs and some circles here, right? So the eyes are circles.
Now, did you say 70 lines for the thing?
I think 70. Yeah, I said 75.
Oh,
So it
okay.
depends. So I put the line minimum in there just to give some sort of context, but you can see that like this one is
Like 300.
way more. Yeah, like
Oh, never mind.
so,
400.
so it depends, right? So it depends on how detailed you want to get with it. So let's go back over here. All right, so I think maybe one of these is a little bit less. Right, so this is 80. All right, so this like you said, Gabe, this looks pretty good, and it's just over the lines here. So I had the same 75. But you could, right, so you could finish. It seems like when I look at this, to me, it looks finished. There's nothing, right, that's glaring. Like, could you add more to this? Sure, you could, but to me, it looks like it's done, right? There's like,
Yeah.
this thing looks like a face. You can kind of, in the class at the time, I could tell who it was. Yep. Other things?
Oh, no, that's about it.
All right.
Yeah, that makes sense.
Yeah, if more things come up, right? So you still have a week and a half or so to go through it. So, whatever comes up, let me know, and then I'm happy to answer them. All right. So one of the things that I asked us to do for today was to think about this article right here, Mathematics of Herd Immunity. So did you get a chance? Jody, I know you're not, I see you there. I don't know if you're chiming in or not. I don't know if you're in the chat. But yeah, you're welcome to comment on stuff too. Put it in the chat if you don't want to, say it out loud. It's okay. All right, so did you get a chance to read this one, Mathematics of Herd Immunity?
Not yet.
No.
Okay. So, Jody, so nobody read it yet. Well, let's take some time. Let's go through together. I mean, it might be good to get it on video too. So I think, so the point behind this article was to showcase, the importance of vaccines in sort of getting a flu shot. And as we can see, like what's happening right now, some of these ideas extend to our current situation. So have you been seeing sort of in the news, like people keep talking about social distancing and the importance of staying at home?
Mm-hmm.
Have you heard this stuff through social media or in the news?
Yes.
Yeah.
Yeah. So basically what I want to do is go through this article and say, so this article is from Quantum Magazine, but it was published. So if we come down here, okay, so I can sort of mark this up in real time if we want to. All right, this was published in February 5th, 2018. And so it just sort of goes through this idea of using exponential growth and exponential models to figure out how disease is spread or how contagions spread. And so the way that Patrick Conacher, the author, he says, well, suppose that you have this situation where you're spreading a rumor. Okay, so there's like a rumor amongst your friends, and the way that you spread the rumor is you just tell one person. Okay, so Gabe, you tell one person, Nick, you tell one person, right? So, and then whoever you tell, they'll tell one person, and then that person will tell one more person. And so if everybody only tells one other person at the end of the month, what he's claiming is, okay, only 31 people will know it if you include yourself, right? So I know it. I told Gabe. Gabe told Nick. Nick told Jody. Jody told somebody else. And then at the end of 30 days, there'll be me plus 30 other people that know the rumor. Okay, so 31 people will know it, which is not too many, right? So that's the kind of the point that he makes right here. Not too many people, but let's suppose that we extend that situation and say, you're going to tell two. I'm going to tell two people, right? So I tell Gabe and Nick, and then they tell two people. So Gabe, you tell Jody and somebody else. Nick, you tell two other people. And then every day, two more people get told. Everybody tells two more people every day. At the end of 30 days, what's going to happen is it's not going to be 31 people that know. It's going to be this number right here. Okay? Okay, so that's 2 billion, right? So 2 billion people. So the difference between telling one person and telling two people is extraordinary, right? It goes from 31 people knowing the rumor to 2 billion people knowing the rumor. Now, it doesn't exactly work like this, right? Because you try to tell somebody the rumor and then they're going to know. So it's not that everybody's new at any point in time. And then sometimes you'll saturate different social circles. But what we're going to do when you go through this article is we're going to think about it and say, hey, it's not just a rumor that you can be talking about. You can also be talking about like spreading a disease or a sickness, right? Like this virus that's going around right now. And so this type of growth that you're seeing, right, when you see it's 2, then 4, then 8, then 16, then 32, this doubling, that's what we call exponential growth. Okay, so this is the whole next chapter in our activities. It's all about exponential growth. And so we have this idea, right? So what's happening, what we're seeing right now in society is the virus that's around us is growing exponentially. So more people, you might hear in the news that it's like, oh, the number of days it takes for the infections to double, right? So that's a very common thing called the doubling time. And so yeah, go ahead, Nick.
What? No, I didn't say anything.
Gabe, are you good? We're good so far?
Yeah, I'm good.
Okay. All right, so this is it's very, I'm going to put this in context here because we're going to study all these exponential functions, and that's kind of what you're seeing, around you when they talk about these models in the news. Okay, so we have this nice graph here that says, you've probably seen some graphics that look a whole lot like this one right here, right in the news. You've probably seen stuff that looks like this with these lines that kind of curve way up, these exponential growth lines. And so when you have, when you have this doubling, right? So you're telling more than one person every day, or you're infecting more than one person every day, you get this growth here. And that's this blue line. And so what we'll see through this whole article today is social distancing. What it does is it makes it so that you don't infect two people. You only infect one person. And so what kind of thresholds do we need to make it so that happens, right? So if we're only infecting one person every day, not so bad. If we're infecting two people every day, it's really bad. Right? So we want to kind of make that idea and see how we can model that with mathematics. Okay. All right, so some notation here. So they introduced this idea of R naught. Okay, so R naught is how many people that you're infecting, right? So the average number of new infections is called R naught. So if everybody is going to tell two people or infect two people, we would say R naught is 2. If, everybody infects on average 3 other people, R naught would be 3. And if you did 1.5 people on average, it'd be 1.5. Okay. So for some context here, diseases in the past, So measles, smallpox, mumps, they have these infection rates. So you've probably heard of measles and how bad it was. Well, it's bad because it's really super contagious, right? So anybody who gets it, on average, they're going to infect between 12 and 18 people, right? That's what this is saying. Smallpox is between 5 and 7. And so the best estimates from the World Health Organization right now are COVID-19 is like in this range. Okay, so COVID-19 is the disease that's caused by the coronavirus. Okay, so we're somewhere down here right now where we have, somewhere between 2 and 3 people are getting infected every day, and we're seeing that, hey, this is the first pandemic of our lifetime. It's not the first pandemic that the world has endured, right? But the last sort of major one was this one in 1918, so almost 100 years ago. Right? And that's kind of hard to put into perspective.
So is it 2 to 3 people infected per person per day?
Correct. So
Or 2 to
per
3
person over the course of their infectious period, yeah. So if you're infected, you are going to transmit it to 2 or 3 other people.
per day? Okay.
No, just you're just going to transmit it to 2 or 3 other people, period.
Total. Oh, okay.
So it's kind of like the rumor telling, right? So you're not going to tell 2 people every day. You'll just tell 2 people. And so it doesn't work every day because, eventually people are going to recover and they're not going to be infectious anymore. So the model, it doesn't make sense to say it's every day because you're only going to infect people like while you're contagious. One of the things right now that is so bad about the coronavirus is sometimes people are asymptomatic, which means they don't have any symptoms. You don't even know that you have it, but you're still contagious and you're still giving it to other people. And so that's one of the reasons why we say this social distancing is so important. Okay. All right. So this article is about vaccines. And so currently we don't have a vaccine for coronavirus, but we still want to keep this idea in mind. Hey, can we reduce the transmission rate to 1? That's the idea. What can we do? What kind of steps can we take to make it so that every person would only infect at most 1 other person? Okay, so that's the whole idea. You want to make it so that instead of infecting more than 1 person, you infect at most 1 person for every contagious person. And then if that happens, things are good. And if that's above 1, things are bad. So right now we're above 1, and so we're trying to get everything back to 1 or less. So usually this is done with a vaccine, but we don't have a vaccine. Coronavirus is totally brand new. And so what we're going to do is we have this idea of social distancing. So we're all at home right now. So we're not going to spread the disease to each other, right? So the fact that we're meeting virtually right now means like I can't, if I'm contagious, right? So if I have coronavirus and I'm contagious, I can't infect you, right? You're not anywhere near me. So it sort of acts as sort of a faux vaccine. And so when we think about vaccines in this case, through the rest of this article, think about it as, instead of a vaccine, think about it as, hey, they just stayed home or they're not around that person. All right, so here's what we call a threshold. So if we think about this idea right here, how many individuals need to stay home or how many individuals need to be vaccinated to bring this number of infections down to 1? Okay, and so what we'll do is we can walk through a model here. Okay, so we're going to assume that, we have this R0 of 2. So every infected person will infect 2 other people, the same as our rumor model. And so what that would mean is if you're this person, right? So if this is you right here, right? So if this is you, you would see, say, 10 other people, for example. And of those 10 people that you see during your infectious period, 2 of them would become infected, right? So that's what I represented with these green dots right here. Okay, so 2 other people would become infected and 8 people wouldn't. doesn't seem like it's so bad, but we saw before, right? If you do this over 30 days with all these people, then really a lot of people become infected. Okay, so the idea is, well, what if we said some of the people couldn't? Okay, so what if some of the people couldn't contract the disease because what did they do? Well, they stayed home, right? I'll make these little houses. So 2 of the people stayed home. So this person who was infectious, what happened? Well, they were, right, they're infectious, but they're not going to, right, they're not going to see this person, and they're not going to see this person because they're at home. They stayed home. But on average, they're still going to infect 2 people. So if we thought about it before, all of the 10 people, okay, so let's make this, let's take our pen again. All of the 10 people up in this, everybody had about a 20% chance of being infected. Okay, so there's 10 people, 2 infections, everybody has about a 20% chance. So that chance, we know that the virus is the same, right? So it has the same R naught. So now with 2 people staying home, everybody still has a 20% chance of being infected. And so what that tells us is, we're not going to have 2 people that get infected anymore. What we're going to have is we're going to have 20% of 8, or we're going to have about 1.6 people be infected. Okay, so just by 20% of the people staying home, instead of having this R naught of 2, we're going to have this R naught of 1.6. We're going to bring that number down, and 1.6 is better than 2. Okay. So 1.6 still isn't 1. So what we need to ask ourselves, okay, if I have an R naught of 2, well, how many people would have to stay home in order to make this work, to get this R naught all the way down to 1? Okay, so what we have here is we're going to end up with an equation something like this. Okay, so 20% of 10, the total people minus the number of people that stayed home. Okay, so this is going to be the R naught. This is going to be how many people we expect to be infected by any infectious person. And so we want to know, when is that number going to be equal to 1? Okay, so how do we bring that R naught down to 1? And so what the article tells us is, hey, if I plugged in 5, right? So if I plug in 5 in here for 5 vaccinations, what that's going to tell me is if 5 people are vaccinated, right, or staying home, then everybody still has a 20% chance out here. And so that means on average, only 1 of these people is going to get infected, which that's where we want to be, right? We want 1 person, that's okay, that's manageable. Okay. Okay, so what we saw was if we have an R naught of 2, then about 50%, right? So if with an R naught of 2, you need about 50% of the people to stay home in order to bring that infection rate down. And so the question is, well, what if your R naught is not 2? What if it's higher than that? Okay, so if it's higher than that, you actually set up an equation that looks a lot like this. Okay, so before, this R naught over N, this was our 0.2 or our 20%, right? So this was what we had, the percentage, right, of the population. N is the number of people, and then V is the number of vaccinations, or in our case, the number of people that are staying home. Okay, so the question is, for any R naught, if we know what it is, right, if we rearrange, the percentage of people that we want to have staying home is given by this number right here, 1 minus 1 over R naught. Okay, so if we can estimate, right, so if we can use mathematical models to estimate how many people get infected on average by a person, then we can calculate the percentage of people that need to be vaccinated or the percentage of people that need to be isolated away from this, just not able to get infected. Okay, and so if this happens, right, so you may have heard this term right here, herd immunity, when you talk about it, right? So when you talk about vaccinations, so if you hit this threshold, right? So if we hit this threshold where we can make this number of people immune or just unable to get it by isolation or something, we said we've reached herd immunity. And if we look at this for the same chart that we did before, right? If you did it for measles, the herd immunity threshold is going to be about 92%, right? So that's like super, super infectious, way up high. You need about 92% of the people vaccinated or isolated to not have a spread. So from the World Health Organization, they estimate that COVID-19 has a reproductive rate somewhere around 2.5. So that was from an article that was published about 2 weeks ago from the World Health Organization. So that tells us that what we're somewhere in this range right here. Now, this is just an estimate, so the actual number could be much higher than that. It could be a little bit lower than that. We don't know exactly yet. So a lot of it is a guessing game. So we're somewhere in this range. And so what that says is, hey, if we're going to make it so that we can get this R naught down to 1, we need somewhere between 50 and 75% of the people to be unable to be infected. Okay, so in our case, we have no vaccines. There's only trials that have just started. Estimates are we're like a year and a half away from a vaccine. So between 50 and 75% of the people need to be unable to be infected or at home, just away from transmission sites. And so right now, that's a hard number to get to. And so like some people, right, if you're a doctor, right, you're going to have to leave. You can't, right? You have to go into work. You have to go. So while some percentage of the population has to go to work, they have to go out, they have to go in and see other people. People who don't, right, if you don't have to go out, if you can stay put, then you can help with this number, right? So whatever you're doing, if you can, right, if you can stay home right now, you really should. And so this is the math behind it. And so sort of that's the end of the article. But it kind of kicks us off into our exponential growth time, right? So we're thinking about exponential functions, and it's really quite relevant to us in our current world situation. All right, so I'm going to kick it over to you all. See if you have any questions about this, about what we talked about, this whole herd immunity threshold, or some of the math behind it.
No, it just makes sense, honestly. But it's like, you only can spread it to 3 more people. You can't spread it to anyone else.
Yeah, but that's a lot, right? So what we said is if everybody spreads it to 3 more people, that number grows really fast.
All right.
So we'll see, right? So I have an activity where we'll do it. We won't do it with like a disease spread. We'll do it with circles, and we can kind of see how things build up from that.
Is that the activity on Plato, right, with Desmos?
Yeah. So it's called circles. So what we'll see is, as these things double, right? When are we going to get to some number of people that are infected?
I tried logging into that, but it wouldn't let me because this is like I'm on a class or something like that.
Okay. All right. So Joe, do you have any questions? So let's see. What about you, Nick? You have any questions?
No, I think that makes sense.
Okay. All right. So what we're going to do is we're going to spend some time thinking about exponential growth and sort of basically this kind of model right here, functions that look similar to this, and how instead of a steady growth rate like linear functions, right, we said always has the same average rate of change. What we'll see is every time step we're going to get a multiple of what we had before. So like 2 times, 2 times, 2 times, something like that. When that happens, then that's what we start calling exponential growth. All right, so if we don't have any questions about this, let's go over to, so I'll just downsize this. Let's go over to our Desmos activity. So I'm gonna switch my screen here. And so Gabe, what you should do is you should go to student.desmos.com. Right, so you should type in to your browser student.desmos.com. And then it should ask you, you should see this screen and it should ask you for a class code. And so the class code is this one, GHDCTH.
GHD.
Yep, CTH.
CTH. All right.
Nick, Jody, you're both good with this?
I'm trying to do it right now.
All right, I got it.
Yeah, so when you join, right, then right, so you can put your name there, and then it will give you some prompts. And so what you can do is go through this now. Oops, sorry about that. From my side of things, I'm gonna go look at our teacher dashboard. So what I'll do is let's go ahead and I'm gonna pause the recording here so you can all get set up, and then we'll bring it back when we have some discussion, right? So I'll give you a few minutes to get into this, start thinking about it, and then I'll bring us back together.
All right.
Okay? All right, so we're gonna go through this circles activity. All right, so some of us are going here. All right, so if we're recording, what I'll do is I'll share my teacher screen. So those of us on YouTube can sort of check this out, what the activity looks like. All right, so on this first screen, we watched a video, and what did you notice? All right, so it seems like we see some notices here, right? The circles keep growing, right? They keep splitting out, they keep jumping, right? And every day, right, or every stage, one circle splits into two circles. Okay, so that would be like the idea of you are telling two people in each stage, right? And how far would this go? So can you all see my screen? Jody, Nick, Gabe, you can see my screen too?
Yep.
Yeah.
And so, right, so as we're going along, what we see is like stage one, you had 2. Stage 2 is going to give you 4, right? So as we said, that number doubles. 3, that doubles again, you got 8. And then stage 4, you're going to jump all the way to 16, right? So we can check this, right? And then we have, right, we have some checks here, which is nice. Okay, yep. And so Peter Dirichlet tells us, hey, right, every time we go to the next stage, we're going to multiply by 2. Okay, so now when we get down here, all right, so let's check in sort of where people are. So we're on slide 4 here. So Grace and Julia are not quite there yet. So so let's go ahead and check this out. We'll check out this. So on Julia Robinson's screen right now. What we're looking to do is figure out sort of what are the number of circles that are going to be in each stage. So this is what we had before, right? 2, 4, 8, 16. In the next stage, it should double to 32. And if we look at Jada's work here, it seems like she's writing it out like this, right? So 2 times 2 times 2 times 2 times 2, I think would be the next one. But what would you all put over here? So Nick, I think you were thinking about this slide. Did you put something over here?
Yeah, 2 to the 5th.
2 to the 5th, right? So this is our new sort of a different way to, instead of writing out 2 times 2 a bunch of times, this is our notation, right? This exponent says, hey, 2 to the 5th, right? We have 5 things here. There's 5 2's. There's 2 and so we could write out 2 times 2 times 2 10 times, or over here we could put 2 raised to the 10th, right? So we could put that in there. Okay, and so I guess they want us to do this, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Seems like a lot. All right, so let's check. And then we're good, yeah. So at each stage, right, we double, we double, we double, we double, we double. So we started, right? So if there's one person that was infected, after the first stage, there'd be 2, then there'd be 4. After 10 stages, you're already at 1,000 people, right? So you'd be at 1,000 people. Now, in our context, the time, right? So how long does it take on average for that person, right? For you to tell 2 people or for you to infect 2 people? I think it's depending on where you are in the world, what countries you're in, but some places it's every 2 days, and some places it's every 3 days. So in our context right now, this would be like at the end of 1 month, right? And so what we'll see is, hey, what happens at the end of 2 months or at the end of 3 months, things like that. So if when you think about 10 here, in our current context, you might think about it as, when we get to 20, that would be 2 months. When we get to 30, that's going to be 3 months. Right? All right. So far, so good here. I see we're moving along. Okay. So any ideas here? So Joe, do you have any ideas on this one here, stage 20? I know you're in the chat here. Bring it up. You any ideas for what we would get? Stage 20, yeah, 2 to the 20, right? So that exponent keeps increasing. So at this one, we'd have 2, right? 2 to the 20 circles, right? And so why do we think that? What do you think? You think you agree with this? You disagree? What do you think?
What, 2 to the 20?
Yeah.
I agree with that.
So why 20? Like we have these exponents here. Why 20?
20 because you multiply by 2 20 times.
Because it's stage 20.
Mm-hmm.
Yeah. So this is our stage number, right? So it should match up. So maybe something like this. Okay. All right. How are we doing with this one? Did we get to this? What do y'all think? 2 to 20 has a lot. Stage 21, the next stage is going to have how many? How many more?
A lot more. 20.
It'll be 2 times as many, right?
Yeah, right. It'll be twice as many. So it'll be twice as many as less. So if it's like, so I don't know what number 2 to the 20 is. Maybe it's like a million. It's probably more than a million. But 2 to the 20 is, if it was a million, then it would be 2 million, right? Twice as much. Yep. It'd be double, right? Oh, 2 times as many, right? Right, so be twice as much, right? It doubles every stage. Okay, so if we were in stage 20, we said it has 2 to the 20. Stage 23, though, if we go out, stage 21 had 2 times as many. Stage 23 will have 3 times as many, 8 times as many, or neither. Jody, what do you think in the chat? Nick, okay, what do y'all think?
I think it's going to be 8 times as many because you're doubling the number and then doubling that number and then doubling that number.
Yeah, so 2 and 2 and 2, you put those together, it makes 8. Yeah. So you're gonna go with Lynn here.
Mm-hmm.
So you said it was double, then double again, then double again.
Mm-hmm.
Something like that.
Yeah.
So 8, yeah. So to go from 20 to 21, you're going to double. From 21 to 22, you're going to double. And 22 to 23, you're going to double. So if you double, that's 2. If you double again, that's 4. If you double that, then that's 8, right? So yeah, you're going to have 8 times as many. Okay. So now I want you all to think about this one. Tell me what you think. When are you going to get to this? What is this number?
Isn't that 1 billion?
1 billion, yeah, right. 9 zeros. So when are you going to get to a billion?
Probably 2 to 100th power.
2 to the 100.
No way, because 2 to the 20th is more than a billion, I think.
2 to the 20.
Yeah, I did that earlier, and I think that's more than a billion.
So let's see what happens. 2 to the 100. Okay, so let's try it out. All right, so we'll bring up Desmos. So Gabe, you said 9 zeros, right? 9 zeros is a billion.
Yeah.
Let's try 2 to the 100. So 2 to the 100, so it gives us this number. Okay, so what this means is it would be like a 1 with 30 zeros after it. Okay, not quite 30 zeros because you're going to have some other numbers in there too, but this would be more than, this 2 to the 100 is more than 1 with 30 zeros after it.
Mm.
And so Nick, you said 2 to the 20, right? So this is 2 to the 20 is more than a million, right? So
okay.
3, 6 decimal places, okay? Okay, so it's somewhere between 2 to the 20 and 2 to the 100. So you think we could go up to this, right? That's 2 million. What's the next one going to be? 4 million, right? Double that. Try it out. Are you all? I don't know what you're doing at home, but plug these numbers into Desmos just like I'm doing here, and see when are you going to get to a billion?
Is it 2 to the 30th?
So let's try. Let's try it together. 2 to the 30. This looks like it's 1 and then has 9, a little more than 9 zeros after it, right? So that's what this means. And then what if we backed that off? What if we did 2 to the 29? What number is that?
500 million ish.
Yeah, 536 million.
Mm-hmm.
Okay, so that's 536 million. And so that's not quite there, but if we go to 2 to the 30th, right, then we get to 1 billion. That's like the first time we would go over 1 billion. Right, so after about 30 stages, we would have 2 to the 30. Right?
100.
30 would give us
Right. To the 30th power.
billion, yeah. Right, 2 to the 30th. So after 30 stages, right, so this doubling happens. After 30 doubling stages, that's when you get to 1 billion. And so if you think about this, right, so in our current situation, this doubling time is like 3 days in some places is pretty common. So if your doubling time is 3 days, 30 stages would be 90 days, right? So after 90 days, it would spread to almost 1 billion people, right? So that's more people that are than in the entire United States. So we just want to keep that in mind, right? Now, this isn't a perfect model, right? Because we talked about before with that article, what's going to happen is, you're not everybody's going to do this, and some people that you would see are either going to be recovered and then hopefully immune, or they're going to, they're already going to be infected. Okay, so does this help this idea of exponential growth and how things double, right? So if we keep doubling, really it kind of gets crazy after a while, right? So you went from 1 to 1 billion in just 30 steps, right? Which could be, in our case, could just be a couple months. So everything that's happening right now, right, it's really, right, that's why people are saying it's important, right? Stay inside, stay home, don't get infected. And what we want to do is you've probably heard this term, flatten the curve a little bit. You heard that through the news?
Yeah, it's like make it like less cases and stuff like that. Start slowing down.
Yeah, so pretty much, if we can spread it out, and we don't really want to overwhelm the hospitals if we don't have to. So there's a couple videos. So for next Tuesday, that's the next time that we're going to meet. But I think it'd be good if we can think more about this exponential growth. And then these 2 articles here, this is a nice YouTube video. I think it's only about 8 minutes, but it gives, shows the exponential growth. And this is a Washington Post article. I don't know if you've seen it before, but it's the most read Washington Post article, I think, in the history of the paper.
Mm-hmm.
So play around with this. They do some simulations for you, right? So how you can sort of see in real time how the spread grows if there's no social distancing in place, and then you kind of get these curves here. And then they give you some examples with people social distancing, so just not moving, like sort of staying home. And then you can sort of see how over time how the curve is much less drastic. Yeah. All right. So read this article, and then we can talk about these. There's a couple of them, and then every time you load it, it's actually running simulations for you. So it's brand new every time you load the page. So check this out, and then check out the other video. So what we'll do on Tuesday is we'll come back and we'll start thinking about some of the sort of mechanical things, like some of our exponent rules to help us manipulate functions. And then if we have some data, right? So if we have like a set of data points, we'll see how could we, find the equation to help us model that set of data. And so that's what we'll do. That's what we'll do next next Tuesday. Okay, so but for this week, right? So at the end of this week on Sunday, we got the web work due. It seems like you already did that, and then email me your weekly reflection,
Mhm.
and then we'll look at those for next week. Okay, and so at the end of next week, our self portrait will be due.
All right.
Okay.
Sounds good.
Questions, comments, anything like that?
Did you teachers ever hear about the pass or fail policy that was going around?
I have heard about it. I know that some committees are gonna talk about it tomorrow. So the only information that I have is that that people are talking about it, and they're gonna talk about it tomorrow. So then we might hear more about it after that. So
All right, I just wanna make sure.
it's not an official policy yet, but some people are thinking about it. As far as I know, no decisions have been made.
All right.
But I mean, is that something that you are interested in? If that was an option going around?
I don't know, just like for other classes, like in the future, like because a couple of my friends at their school are doing it. Like, I guess they can pick whatever classes they want to like pass, I guess, or if they want a letter grade or not.
Yeah, all right. So I think the option would be you can opt to make it pass or fail, or you can opt for letter grade.
Yeah.
But yeah, that hasn't been mandated by our university yet. I know other schools are doing it though.
All right.
So
I just
think
wanna-
it would only apply to this semester though. So I don't think it would go.
Yeah. I just wanted to make sure because I got like a bunch of emails about it from like people.
From people at the university.
Yeah.
Yeah, I think something got sent out to university communications. I don't know if you get those emails.
Yeah.
But yeah, it's something that's being talked about.
Okay.
Anything else?
No.
Yeah, take a bid.
Nick's good.
Mhm.
Cody, you're good. All right, so hopefully this was informative today. I know you probably hear a lot about it, but just to give you another perspective about the math behind everything that's going on. Yeah, stay inside, stay safe, and I hope you're all doing well.
All right.
So we'll check in next Tuesday. All right, so next Tuesday, same time, we'll meet over Zoom.
Sounds good.
All right.
All right, see y'all
Have a
then.
good day.
You too.